Assalamualaikum and hi. My name is Aziza binti Arfian and I'm going to present my research proposal entitled Analyze the Methods of Numerical Integration in Calculating Area under the Graph. This research starts with research background where we will discuss about definition of integration, the method of integration and so on. In general, integration is a tool for calculating much more than areas and volume. All these calculations will be computed by follow the basic of integral concept and various integral formulas and techniques such as by-part and tabular method and so on. The appearance of more complex problems makes the integration process more difficult, and this leads to the issuance of a new method of integration, which is the numerical method. Then, this requires us to introduce the method of numerical integration, or also known as numerical approximate of definite integrals. Hence, this research proposal will be discussing about how numerical integration provides ways to compute an approximation of area between functions graph and the x and y axis, also choosing which method is more accurate. This research come out with problem statement. The use of finite sum methods in solving area under the graph will expose us to absolute errors during calculations. This is because the method will estimate the area of the graph based on the strips that have been divided into small strips. Therefore, we will analyze three methods of numerical integration, which are trapezoidal, Simpson's, and Gaussian quadrature. This research proposal have four research objectives. First, to perform the method of numerical integration in solving area under the graph. Second, to make comparison between the method of numerical integration and analytical solution. Third, to analyze the error of each method of numerical integration. And then the fourth, to evaluate the problems that face on numerical integration using MATLAB software. Significance of study. This research project will eventually lead to a better understanding, especially on how to compute the function that present in the graph using the numerical solution. Also, in this project, we will also discuss about how MATLAB software is used and how the algorithm created. This research proposal consists of 5 chapters. The first chapter is introduction. The second chapter is the literature review, where we will review on previous study of area under the graph, which includes numerical integration. The third chapter is the numerical integration. The fourth chapter is the expected findings, where we will discussing what is the expected finding after conducting this study. And then the chapter 5 is the conclusion, where we will conclude, we will brief a short discussion of this research project. Chapter 2, Literature Review. This literature review consists of several discussions. So the first is we will discuss about numerical integration of area under the graph. So we must know what is numerical integration. In generally, numerical integration is simply a procedure that approximates an integral by a summation. So we can recall the integral form is I equal to integration from a b fx dx, where this integration we can view graphically as the area between the x-axis and the y-axis. And for information, the y-axis is presenting the function of the problems. So, the basis of formulating the finite integral is the construction of appropriate finite sums. But there is no simple geometric formula for calculating the areas of general shapes that having a curved boundaries. So, we will use rectangles to approximate the area under the graph. So this method called finite sum. So let's we took an example where y is equal to 1 minus x squared. So we approximate it as areas approximate equal 1 dot 1 over 2 plus 3 over 4 dot 1 over 2 equal to 0.875, where the estimation is larger than the true area since we only use two rectangles. To get more better approximation, we can take more rectangles applied into the function and we will get more we will get the solution approach the real solution. Besides that, we also have another method to approximate area under the graph, which are trapezoidal, Simpson's, and Gauss quadrature. For trapezoidal rule, the area under the curve between the bounds of A and B is simply approximated by the sum of multiple evenly spaced trapezoids using the trapezoidal rule of numerical integration. The head of a trapezoid is found from the integrand and evaluated at equally spaced points xj and sj plus I. Besides that, Simpson's rule will also work same as trapezoid rule. However, Simpson's rule will use a polynomial quadratic or cubic to estimate the curve. Besides that, we also have another method, which is Gauss quadrature, where this method is very different from the two methods, and we will discuss more in the next chapter. In this chapter, we will also review on MATLAB software. So MATLAB is the short form from Matrix Laboratory, and due to this, MATLAB's only focus on metric calculation. So the original version of MATLAB was a straightforward interactive matrix calculator rather than a programming language. So programs, toolboxes, and graphics were absent and not even ODE. Therefore, in keeping with our current developments, the founders of MATLAB made some improvements to this software where they call as modern MATLAB. Next chapter is numerical integration, we will discuss about the method of numerical integration. The first is trapezoidal rule. The trapezium rule is the simplest numerical integration using the polynomial of order 1, y equal to p1x, or we can say that it is a straight line method. So by using Newton forward difference interpolation, we will get the formula like this. P1x equal to f naught plus r difference of f naught, where r is equal to r equal to x minus x naught over h, where h is the step between of 2 points. After we doing a derivation of the formula, we will get the area of trapezoid ABCD, or generally, this formula we will set as trapezoidal rule of integration. As you can see on the left screen, there is a figure of linear approximation where we only use one trapezium. So, to improve our solution, we can improve our solution by dividing this interval into a small number intervals and applying the rule of each of these subintervals. Then, we can see the derivation of trapezoidal rule like this. And this is the general formula, and we call as composite trapezoidal rule. Then, we also can compute this trapezoidal rule by using MATLAB. So here is the algorithm for MATLAB. So we must define what is f, a, b, and n. And we substitute h is equal to b minus a over n. Also, we substitute the formula of trapezoidal rule. And then we substitute the integration from A to B. After that, if we run the program, we will get the value of fx on AB. Second is the method is Simpson's rule. Simpson's rule using polynomial, quadratic, or cubic function to approximate the function given. Here is the general function, the general polynomial equation p2x equal to f naught plus r difference f naught plus r minus 1 over 2 factorial plus square of difference f naught where r equal to x minus x naught over h. And we derive the formula, we will get the Simpson's rule. So as you can see on the left of the screen, we will see the figure of quadratic approximation. So we can improve this solution, or we can get a better solution by improve this solution, or improve by dividing this interval into several small intervals and applying the rule to each of these subintervals. So we will get the new formula, which is we known as composite Simpson's rule. So on this side is the even subinterval, and then this side is the odd subinterval. Besides that, we also can compute the Simpson's rule by using MATLAB software. So we sub in what is h, what is m. Also, we must to sub in the formula of odd subinterval and then even subinterval. After that, we sub in the formula of integration from a, b, and then we can get the value of the function of the area under the graph. So, the third method of numerical integration is Gaussian quadrature. So, to use this Gaussian quadrature, we must to transform our interval from a, b to -1 and 1. So, it's only have one range, which is -1 to 1. After we derive, we can consider the integral of the form like this. So we call this is n-point Gauss quadrature. So let we take an example of 2-point Gauss quadrature. If we use 2-point Gaussian quadrature, we will only have C1 and C2. Also, our nodes also have T1 and T2. C1 and C2 are the ranks of the Gaussian quadrature. We derive the formula, and hence we have the new formula of 2-point Gauss quadrature. Besides that, we also can use 3-point Gauss quadrature. So this is the general formula of 3-point Gauss quadrature. After we sub in the formula into the general n-point Gauss quadrature, so the new formula become like this. And besides that, we also can use the table of Gaussian quadrature to find more nodes, or to find more I, to find the n, whether n is equal to 3, 4, and more. Besides that, this is the algorithm for Gaussian quadrature, where we begin the computation with the for loop. Means that we must to have the function if and n. The fourth chapter we discuss about the expected finding. First is error-bounds formula for trapezoidal rule. So this is the common trapezoidal rule, and then the estimation error is below. So for trapezoidal rule, we will differentiate twice. Then the error bounds formula for Simpson's rule is quite similar as trapezoidal rule, but the main difference is we use the fourth derivative at here. So BA is the endpoints of cross intervals and N is the sub-interval, the number of partition, the number of sub-intervals. Then for Gauss quadrature, in general, we consider formula for Gauss quadrature as below, where Ci is the weight and we define Ci like this. This equivalence of this formula for the weights GTI can be seen from the fact that difference of ln minus 1 ix square minus ln minus 1 ix is a polynomial of degree 2n minus 1 that is divisible by pi and x because it vanishes at all of the nodes. So we can say that the area is equal to the integration a b g x dx minus the summation from I equal to 1 to n ci g xi. In addition to this area formula, we can easily obtain qualitative bounds on the area. For example, if we know that the even derivatives of g are positive, we know that the quadrature rule yields a lower bound for the Gauss integral. Similarly, if the even derivatives of g are negative, then the quadrature rule gives an upper bound. In conclusion, if we compare the area obtained by trapezoidal rule and Simpson's rule, we can analyze that Simpson's rule more accurate than trapezoidal rule. This is because the high derivatives we take, the more accurate solution we can get it. Because trapezoidal rule only use the second derivative, but Simpson's rule used fourth derivative. Besides that, we also can see the area of Gauss quadrature is less than trapezoidal and Simpson's rule. It's shown that this formula may give more accurate solution towards the actual solution when defining area under the graph. Also, to find the area formula of Gauss quadrature, we use spatial computation of weight. That's all. Thank you for watching.